Alright, so this is the last section, 7.4, which is on checking assumptions and transforming data. So let's first talk about checking assumptions. And we need to talk about what assumptions are. So these assumptions are for the linear model. So remember that the true line has the equation yi equals to beta 0 plus beta 1 xi plus epsilon I, where epsilon I is the error. And the assumptions we're talking about is the assumptions and the errors. So the assumptions are that epsilon I are independent, normally distributed, all with mean 0 and the same variance. Okay. So it's important that these assumptions are satisfied. That's the way to prove that our linear model is good. But there's no way to directly check the assumptions because we don't know the values of epsilon I, but we know the epsilon I in the least square line. On the least square line, we have yi equals to beta 0 hat plus beta 1 hat xi plus ei. And ei is called a residual. So instead of looking at errors, we can look at the residuals instead. Because we know the values of residuals, so we can look at it instead. So what we're going to do is going to do what's called a residual plot. So the residual plot is basically we're plotting ei against yi hat. Yeah, so basically we have two axes. The horizontal axis is x, yi hat, and the vertical axis is ei. Okay. So suppose we want to check if the assumptions hold. We look at the residual plot, and if two things hold, then the assumption is true. Actually, technically, if the two things hold, then it's likely, not for certain, but likely that the assumption holds. Okay. So the two conditions are the residual plot has no trend or curve. And the second condition is what's called the plot is homoscedastic. I'm going to explain what it means right away because it's a new word. So homoscedastic means that the variance of ei doesn't change, doesn't vary much when yi hat changes. Okay. And the opposite of homoscedastic is heteroscedastic. Okay, so it's probably faster to look at some examples and notice that this is purely visual inspection. There's no quantitative way to determine if the plot has no trend or curve. It's pretty much depends on who looks at it and what trend and curve mean for the person who looks at it. So this is basically by visual inspection. Okay, so it's not really accurate, but so let's look at some examples or non-examples. So this top one is an example, and the bottom three are non-examples. Okay, so if you look at the first and the third one, the first and the third one are not homoscedastic. Because if you look at how far the dots are from the zero line, you notice that the further the dot to the right, the further the dots are away from the horizontal axis. So there's the variance grows bigger. So variance grows as y hat grows. And it's the same for the third graph because variance also grows as yi hat grows. In the middle one, how far the dots are from the 0 doesn't seem to depend on the yi hat, but it shows a trend curve, so it looks like there's a trend, right? So for the residual, let's use EI. EI is positive for yi hat in the middle, but EI is negative for yi hat large or small. So that's a trend. So that violates the first condition. And if you look at other books, this technical term shows trend is equal. We call this graph biased. So this is the technical term that's not introduced in our textbook, but in other books it's called biased. Okay. And the example on the top left is perfectly drawn. There's no trend or curve. The dots are pretty much scattered evenly, and if you look at how far the dots are from the 0, then you notice that there's not really. It doesn't grow bigger or smaller as yi hat grows. So this is definitely homostatic. Yep. So that's it about the residual plot. Just a warning. This is very objective. Yeah, this is very objective. So keep in mind that it's not really a precise criterion, but it helps you to determine whether the linear model is good or not.